Okay, so this week we're going to do resonance of RLC circuit, meaning that the circuit has the inductor, a resistor, and a capacitor. And in activity 11, you learned the when you have the AC circuit connected to different electrical elements, there's a there's a term we call the inductive reactance. We have the capacitive reactance and also resistance, and these three resistance are equivalent in a way equivalent to each other, but dealing with the by applying to different electrical elements. And so when you have the AC circuit, you have the current that is a function of time, and that's equal to the voltage as a function of time over impedance, which is the equivalent to total resistance of that circuit. And so, so we know that the voltage can be described by sinusoidal function. So you have like this, the amplitude times sine of omega t, and omega, of course, is the angular frequency. And impedance is equal to the square root of R squared plus the difference of these two reactance square. And so just give you, just remind you that XL is equal to omega times L, XC is equal to 1 over omega C, meaning that these two quantities are frequency dependent. And if these two quantities are dependent, meaning that your Z is also frequency dependent, okay? And omega is equal to 2 pi F. So, because, these are frequency dependence, and so at high frequencies, which means that, when the frequency is high, your XL, because it has expression omega times inductance, we know that the XL is greater than XC. And so the phase angle is positive. And what does that mean? The phase is very important. The phase angle, if that's positive, it means that current lags the voltage. At low frequency, on the other hand, XL is less than XC, meaning that the phase angle is negative. If the phase angle is negative, it means that current leads the voltage. What happened when XL is equal to XC? So when XL equals XC, if you look at this equation, it means that XL and XC cancel each other. And so your Z, the impedance, is just equal to R, meaning that when those two reactants are equal to each other, the phase angle is zero, meaning that they are in phase. They're in phase, and also the impedance is equal to resistance of the resistor. If that is the case, meaning that your Z is the smallest value that it can attain, because these two just cancel each other. When Z is the smallest value as possible, which is equal to R, then your current will become a maximum value. Okay, so when XL equals XC, it means that Z is equal to R, and your I is a maximum value. During this condition, we indicate that the circuit is in resonance. Okay, and that frequency, because those two quantities are frequency dependent. So there's one frequency that will make XL equals XC. When that frequency is equal to a specific frequency, that frequency is called the resonant frequency. And how do we find that resonant frequency? That resonant frequency is when we call that natural frequency of oscillation for LC circuit, where there's no resistance. Then omega naught is equal to 1 over square root LC. So we can see that the natural resonance frequency does not depend on voltage, does not depend on current. It only depends on the magnitude of inductance and also the capacitance of the capacitor. Okay, so several things happen when the current is when the circuit is in resonance, meaning that your current becomes a maximum value, and also the XL is equal to XC and Z is equal to R. Okay, so in other words, the RLC circuit, then the circuit is like only have the resistance of the resistor in effect, and the XL and XC, they just cancel each other. What about the, when we're dealing with the AC circuit, we usually are more interested in knowing the average power. So the average power of the circuit can be found by using this. So the average power is equal to the root mean square value of current squared times R. And then realizing that your I and voltage are related to this, you'll find that the average power has this expression, which is the root mean square value of voltage square times the resistance times the omega square over this term. If you recognize that is that's basically similar to the Z value. Okay. So you have the, so you can see that your average power also is frequency dependent. But if the circuit is in resonance, meaning that omega, this omega, which is the one that you can change externally, if this omega is equal to omega naught, which is the natural resonance frequency, which can be calculated using equation 2, then you will find that the average power will just be this term, of course, is cancelled, and then your R here, R there, so you just have the and then omega square, they just get canceled. So the average power would just be the root mean square, the voltage or the root mean square of voltage square over 1R. Okay, so that's basically when the circuit is in resonance, then this is how you calculate the average power. And so, during when you're dealing with the electrical circuit, there's one quantity that is very important that indicate whether the circuit is a good circuit or not. When I say good circuit, applying to, for example, the radio, when you want to use a radio to receive, information or signal, you want the quality factor Q to be as high as possible, because that indicate how good the circuit is, how noisy, how not so noisy that circuit is. Because when you play with the radio before, you'll find that sometimes it's very noisy, and it has to do with the quality factor. If Q is high, then you will have a much clearer signal. So how do we calculate the quality factor? To calculate quality factor, this is basically how you calculate that omega naught, which is the natural resonance frequency, over delta omega. So what is delta omega? Delta omega is the width at half maximum, which we're going to show in the next on the next page. So delta W is just basically the width of a half maximum, and then this can be approximated by using this equation, omega naught times L over R. So in other words, when you have the LRC, you can just use the those values to calculate the quality factor. Okay, and so usually, let's see, high Q circuit corresponds to a very narrow range of frequencies, and a low Q corresponds to a broader range of frequencies. And the typical value of Q is about like 10 to 100. The higher the Q, the better. And so, what does that mean when we talk about when you have the high Q? It means that it has a narrow range, because when you have a high Q, meaning that when you have a high Q, if you just come back to this equation, when you have a high Q, it means that R is small, and so this is the diagram, shows the average power as a function of the frequency ratio, in relation, like omega naught over omega. So when you have a smaller R, you can see that this is much sharper. When this is much sharper, meaning that the delta omega, which is the value at half max, the width at half max. So this is the peak, and at the middle half max. So, and this is the width. Okay, the width at half maximum. This one, you can see that when you have a smaller R, this is smaller. When you have a larger R, you have a larger delta omega, which covers a broader range, which we don't want. We want the signal to be as clear as possible. So so smaller R would achieve this. And this is basically tells you that at high frequency, which is on this side, at high frequency XL is greater than XC. At low frequency, XL is less than XC. And what about when the ratio is equal to 1? When omega is equal to omega naught, it means that you have reached the resonance frequency. And when you reach the resonance frequency, the power will give you the maximum power, which is what we want. Okay. And we also mentioned, I think in previous experiments, you've learned that the Riemann square value is the maximum value over square root of 2. And so this diagram just shows you that when you have a waveform, this VP indicates the peak value, and VP to P is the value from peak to peak. And but sometimes we don't want the peak value. What we want is the Riemann square value. So how do we calculate the Riemann square value? Is basically just equal to the peak value over the square root of 2, which is this one. Okay. All right. So the experiment is set like this, very simple. You have the RLC circuit, and so you have the inductor, you have the resistor, you have the capacitor, and we're going to connect this to the function generator, and we're going to change frequencies, and then this we're going to measure the voltage. We're going to measure the voltage across the resistor, and then output it to the oscilloscope. So in the oscilloscope, you're going to see this kind of diagram. And this is the in the XY mode. One is the output voltage, and one is the voltage of the resistor. And because this is an AC circuit, which means that your voltage can be voltage is a sinusoidal waveform, and the output voltage is also a sinusoidal waveform. So and they may be in phase or may not be out, maybe in phase or out of phase, and the goal is to find the place to change your frequency. So so they are in phase. And how do we know they are in phase? Basically, we will go by the Lisa Joule figure, which is like this. And you can see that this is an elliptical form, and we want to get to the when the output voltage and the voltage across the resistor has a 1:1 ratio, it's going to give you a perfect circle. So so we'll start from there, and then we're going to change the frequency until it becomes a straight line, a linear line. And when it becomes a linear line, it means that both the output and also the voltage of the resistor, they are in phase, and that is the condition that we want. And so the diagram will look like this. So when you change the frequency until you reach a straight line, this indicates that you have matched the other frequency that will produce this kind of straight line. They are in phase, and then you'll be measuring the voltage first peak to peak, and then calculate the Riemann square. Once you have the Riemann square value, then what we want to do is that we want to use the Riemann square voltage to calculate the average power. And once you calculate average power, you want to reproduce the plot like this, that the average power as a function, and then plotting the ratio omega naught over omega. Okay, so that's pretty much what you want to do. Just change the frequency, and then when you reach a straight line, indicate that you have found the right frequency, and then you measure the voltage. And so the average power, because we're matching the frequencies until they are in phase. So to calculate the average power, instead of using equation 1, you can just use you can just use this equation. That is the average power is equal to the Riemann square value over R. Okay, and once you have that, then you will be able to plot the plot figure like figure 1. And so that's basically what you want to do. And let me bring up the table, the data that you're going to see. So the data, you'll be providing two files. One is the Word document. So this Word document provides the capacitance value, which is 991.5 narrow farad. So you need to convert that to farad. Okay, narrow is 10 to the negative 9th. And then inductance has the 8.064 millihenry. Milli is 10 to the negative 3. And then, so in the activity, it says that we're going to use 3 different resistor value, but we'll just be doing 2. So you don't have to do the 100 ohms case, just do the 4.7 and 33 ohm. So so for 4.3, the measure value is this. For 33, the measure value is this, and the measure frequency will for 4.3, for 4.7, you have this value. For 33, you have this value. So based on this, you want to calculate Q. And if you remember, your Q is equal to omega naught times L over R. And you can use the measure value to calculate the Q. And the L is this value. Make sure that everything is in SI unit. Omega naught, you have the F naught, and omega naught is just 2 pi times F naught, okay? And theoretical value of F naught, so these are the measures you're going to compare to your theoretical. So the theoretical, you will use, you will calculate omega naught first. That will be 1 over L square root of LC. And once you calculate that, divided by 2 pi will give you F naught. And then you're going to compare to the measure value to get your percent error, okay? And the VP, the source voltage is we output 1, and the root square, of course, is just the square root, this over square root, so that's 0.707. This is the output voltage. For the voltage across the resistor, we are using this, okay? So so again, ignore the columns for the 100 ohm case, and then so for this you have you do not. For this one, you complete, for this file, you complete this, or if you set it up on your Excel to make it look like this, that will be fine, okay? And make sure that you have the border on, because otherwise it will be very difficult once you upload to the file, to Canvas. Some of the format may not be exactly what's shown there. It will make it difficult for me to actually see which one is for which. Now for this table, you do not have to fill out the table here because you're going to use Excel. And this basically tells you that the frequency ratio is from 0.85 all the way to 1.15. So let me bring up the Excel file. So another file you'll be given is Excel file. And this Excel file, I already have the other 2 columns. So the 2 data sets. So your R here, we're going to use the measure value, so 4.689, and the R is another one, 32.59. F naught, which is the measure value, you have this one and that one. So you need to calculate the F value. So basically F value will just be this, 1,777 times this column, and just drag it down. Calculate the first value, and then move your mouse until you see a solid cross, drag it all the way down. Then you will be able to compute that automatically using Excel. Do not kill in your calculator, because it's going to take you, I don't know, if you have to do all this, that would take you probably 20 minutes or 15 minutes, because you have to like punch in the calculator and then key it in. You might as well just use Excel to do that. If you don't know how to do it, go ask other students. All right, and then VP value are given, okay? So this is for under this 4.689 case. So you want to use Excel to calculate the root square of the value, which is the VP over square root of 2. And then for the average power you will use the root this value square over this value, okay? So then and then you'll calculate the average power. Once you have the average power, what you want to do is that you want to plot. So you want to plot the average power versus this column, F over F naught. Yeah, you don't have to calculate omega over omega, just do the F over F naught. So you would expect to have one curve and then another curve. So I would, instead of doing 2 figures, I want you to do 1 figure, have 2 curves on 1 figure. So you can see immediately which one is, and then label that, what value is this R and what value is that R. And you can see immediately that, when you have when you have a smaller R, you should get actually a narrow curve like this, and the other one will be like something like this, okay? So in other words, I wanted to put two curves on one figure, so you can see it, emits directly, and compare those two curves, okay? So that's basically what you want to do, and if there are questions in the data analysis, then answer the questions as much as you can. All right. I know you probably have not yet learned RLC circuit, but regarding data analysis, and also the concept that that those concepts are actually building on from previous lab activities. So you should know what is peak value, what is Root square, and average power and things like that. All right. Okay.